Assalamualaikum wabarakatuh, and good morning to everyone. This is the offline lecture of lecture number 3, WIA2004 operating system. So today's topic is going to be memory management or virtual memory. So we have four. One is page allocation. One is demand paging allocation, segmented allocation, and a combination of segmented and demand page allocation. So before this, we early memory management, we learn about the contiguous, contiguous, where all the all the jobs have to be stored into the memory contiguously, meaning that following the sequential of the main memory. So so this also, because of the virtual memory itself, it eliminates the requirement that the entire program resides in memory during execution. This will save a lot of processing overhead in the main memory. So virtual memory in a thing is a good way of memory manager in operating system. So we're going to learn about the first one, the page memory allocation. An incoming job is divided into pages of equal size. Sector block or a section of a disk. Okay. This is the term that we use for the page memory allocation. Page frame, a section of a main memory. So this is a section of a disk or a secondary storage. Page frame, a section of main memory. This one in the RAM, in our RAM. So secondary storage can be hard disk, HDD or solid state SSD, solid state drive. Yeah. For efficiency, page sectors and page frames are of the same size. So for this particular, for these courses, we just assume that the sectors and the page frames are of the same size. Okay. One sector holds one page of job instruction and fits into one page frame of memory. So we have one sector here, one page of job fit into one page frame of memory. We will see the example of this. Okay. So before we continue, before executing a job, the memory manager usually determines the number of pages. Okay, the number of pages a job, locates and then check whether there is enough empty page frames in the main memory. Okay, first locate the number of pages, how many jobs, how many pages, and then it also checks the empty page frames in the main memory. And if it fits the main memory smaller than the main memory, it will load the page. So it's not necessarily contiguously or following an order, okay, or just side by side. So it will load the pages. So this is page memory allocation. So the disadvantage of this scheme is memory manager must keep track of pages of a program, increase size and complexity of OS. So always have to keep track of pages of a program or applications. So this OS will have to be burdened with more complexity and more overhead. Memory manager use three tables to keep track of pages, which is one is a job table, page map table, and memory map table. This is in the RAM, and this is in the secondary storage. These two is in the secondary storage. Okay, you have a job table and you have a page map table. So you have this one is a job one, first 100 lines, page 0. Okay, you have here job 1, page 3. Okay, and then you have a second 100 lines, page 1. Install job 1, page 1. And then you have a third 100 lines, page 2. You put in job 1, page 2. And remaining 50 lines of page 3, you put here job 1, page 3. So you have here all these. The first job 1 is like divided into four. We call it subroutine or a frame. Sorry, we call it page. Page 0, page 1, page 2, page 3. So each have 100 lines or 100 byte or something. Okay. So page 0 you put here. Job one, page 0, and then page 1 also. Page 0 is on the job 1 page 0, job 1 page 1, job 1 page 2, and job 1 page 3. So this is a page frame number where 0 and 1 is taken by the OS, 2 until 12, or 10 page frame number is free. So any jobs will be stored in this main memory and not contiguously. Okay, it will looks on the empty slot of this in the RAM page frame number empty slot, so it will fix that. So advantage of storing memory okay, before we go that, advantage of these storing programs in non-contiguous location memory is used more efficiently because an empty page frame can be used by any page of any job. So any page like job 2 coming in, so you can fill in any of the empty page frame number. No need for compaction. Okay, you learn about the compaction where any like external fragmentation will be compact. So it reduce the complexity of OS. Okay, job 2, job 3, and so on, divided by page 0, page 1, page 2, and job 3, page 0, page 1, page 2, page 3. Okay, so they will go any of the empty frame in the main memory. So let's say job 2, you have like, let's say goes to the frame number 2, job 2 page 0, this one job 2 page 1, and so on. This one job 2 page 3, and this one job 3 page 0, job 3 page 1, job 3 page 2, and so on. So you have here, this is the advantage of uh, uh, memory used efficiently because you doesn't have to because it is programmed in the non-contiguous locations. So a job table, this is a job table, and this is a page map tables location. This is a location, the address location. So you have here job size 400, your 96, 200, and 500. This is the initial state. So a job table has two entries for each active jobs, and the job sign memory location where its PMT is stored. So this is second job's end. So this is information. So this one 200 and second job's ends, and then from the next job is inserted into the table, into the job table where this is job size, and this is the page map table location. So this like job page 0, 8, job page job page 1 is page frame 10, job page 2 or page frame 5, and job page 3 is page 11. Okay, this is based on the slide number 6. Okay, slide number 6, this one. Okay, you can see like job page 0, job 1 page 0 at 8. So if you can see this, page 0 at 8, page 1 10, page 2 5, job number 1. Okay, and job page 3 is at the page frame 11. Each active job has its page map table containing the information for each page number, and its page frame memory address. So this is a page number, and this is a page frame memory address. So we go to the this is a job memory table. Okay, uh, Memory map table has one entry for each page frame listing the location or free busy status of each. Okay, you have job 1 here, you divide into page 0, page 1, page 2 and page 3. So page 1 have 100 we call it the program 300 number 0 by the system. The programs contain 350 lines here from 1 to 350. But page frames start from 0 and the first one until 99, so it's 100 lines. Page 0, page 1 also 100 lines, start from 0 to 99. Page 2 also 100, and page 3 is 0 to 49, 50 lines. Okay. So this is what we call a displacement or offset of a line. How far is it from beginning of page? It's used to locate that line within its page frame. So line 0, line 100, and line 200 and 300 are the first line for page 0, 1, 2, and 3. So this the first line of page 0, first line of page 1, first line of page 2, and first line of page 3. Okay. Each has displacement of 0. If the OS needs to access line 214, it goes to the page 2. So let's say the OS needs to access location 214. 214, you know, in the page 2. So 214, and then it go to the line 14. Let's say this is line 14. 0 to 14 is go to the line 14 or the 15 line. Okay, 214. So this 214. The first line of VFH has a displacement of 0, the second line displacement of 1, and so on. So this is just a displacement. You assume like 1 is replaced by 0, displacement 0. So demand. So this what is demand paging? This is the second term. Demand paging loads only a part of the program to memory for processing. Okay, only part of program to memory for processing. A job is divided into equally sized pages that initially resides in a secondary storage, your hard disk. When the jobs run, its pages are brought into memory as needed. Allow user to run jobs with less main memory because you have a secondary storage. Uh, you do not utilize your main memory, so you do not make you can make it more efficiently. Secondary storage becoming your virtual memory. So it requires high speed direct access storage device that can work directly with the CPU. Okay, directly with the CPU. Important because pages must be passed quickly from secondary storage to main memory and back again. So you have here like your CPU, and then here your memory, your RAM, and this is your secondary storage. Okay, so page must be passed quickly from secondary to memory and back again. So RAM is fast but small, secondary storage is big but slow. So it is important to minimize the swapping between the secondary storage and the RAM. How and when pages are swapped depends on predefined policies that determine when to make room for needed pages and how to do so. Okay, so you have to predefine policies like first in, first out, least recently used, and so on. We will look on it after this. So the OS relies on the JT, PMT, and MMT to implement the algorithm. Okay, so you have your job table, you have your page map table, and you have your memory map table. Okay, job table, page map table, and memory map table. So just job. So this is a job table, job size, and PMT location. So let's look on this. Okay, you have a job 1 which is divided into 4 pages, page 0, 1, 2, 3. So this page 0, 1, 2, 3, the status yes in memory or 1 1 1 1 1. 0 mean it's not in the memory. So you have here modified, whether it's modified or not, and whether it's reference or not, and page frame number 5. So let's see page 0 job 1. Page 0 job 1 is on the page 5. So job 0 P0. Okay. Modify reference later we will learn in the next example. So status yes or no, 1 or 0, whether it's in memory or not. Modify whether if it's in the memory, if the content has not been modified, it need not be rewritten to secondary storage. So if like the main memory is not modified, you don't have to swap into the or read or write it on the secondary storage. And reference is like the to show that which page are active or inactive for this processing activity. So this is used for least recently used or page swapping policy schemes to determine which pages should remain memory and which should be swapped, which we will look on the example after this. Okay. So here you have here, okay, all here you have here this one. So until page 2 job 4 is 15. So all these page 3, 4 and 5 have to wait until it's one of the page frame is empty. So to load page 3, let's say there's a load page 3 on job 4. Load page 3 on job 4. A resident page must be swapped into secondary storage. So this is the secondary storage. Okay, one of the resident memory page must be swapped into secondary storage. The resident page is copied to secondary storage if have been modified, and page 3 is written into an empty page frame. So let's say in the main memory, any of this value has been modified, it will be swapped into the secondary. It will be written in the or copied into the secondary storage, and page 3 can enter one of the empty page frame number. Okay. So all this is the job. So this main memory processes it. Store it. CPU will execute. After the job is finished, any of the page frame can be freed. Okay, and the page 3 job number 4 can enter one of the main memory page frame number, the free one that already been freed after any of the jobs already processed or already written into the secondary storage. So you have a lot of page swapping policies: first in, first out, first in, last out, round robin, and so on. But we're gonna learn about two popular policies that are always used in the virtual memory management. First one is the first in, first out. As the name suggests, the first one that already in the memory will be the first one to be freed when any new jobs coming in. And least recently used. Okay, least recently used. Anyway, FIFO swaps a page that has been a memory the longest, and least recently used swap a page that is least recently accessed. Okay, as the name. If you forgot how it works, just refer to the name. First in, first out. Least recently used. Okay. Remove the page that is least recently accessed. So you have here when a program calls for page C. Okay, when a program page A must be moved out to make a room for it, solid lines. Okay, let's say page C. So let's swap page A. So like let's say page C want to be in and need to be entered into the page frame 1. Page A here previously must be swapped. Okay, swap page A to be moved out to the secondary storage out to make room for it, solid lines. And then let's say when page A is needed again, it will replace page B. Page B, let's say page A move out, and then page A need to be reload again in the main memory. It will goes into the page B. This is first in, first out. So first in, first out. Okay, and then it will remove page B to the secondary storage, and page A will reside here. Okay, so this is first in, first out. Meaning that first the A coming in, B is the first in, and then when A has need to come back, B has to go out because B is later than page. Not later. Page B enter the page frame first, so it has to be moved out. Okay. This is an example for you to. This is a better example for you to understand. Let's say we have here. Okay. Let's do this one. Okay, we have here A, B, A, C, A, B, D, B, A, C, D. So I'll make an empty one so that you will not be confused. Oh, this is D. Okay, this is D. D, B, A, C, and D. So the first one, A. This one is page frame 1, page frame 1, and page frame 2. Okay. So A has to come in. Okay, A has to come in. So page frame is empty. So this is job to be processed is page for the following order: A B A C A B D, A B A C A B D, B A C D. So when both page frames are occupied, each new page brought into memory will cause an existing one to be swapped out or secondary storage. Okay, the first one A, page frame 1 and page frame 2 is not occupied, so A will enter page frame 1 first. Okay, this is A. So it will cause a page swap or page fault. We call that in any technical names called a page fault. Okay. Okay. For the second one, page B need to enter, and page frame is not in the memory, so B has to be swap. B has to be entered into the page frame 2. So it's not in the memory, so this is B. The current one is A and the new one is B. B is entered. So this again is a page fault because a new we call that a new what we call that jobs to be processed is A B A C A B D B A C D. So B need to enter the page frame 2, not in the memory, so it becomes a page fault. Okay, now ABA. Next one is A. So A, so this one is B. So this one, because A already reset in memory, it is not interrupted or page fault happen. So this is a normal one. Okay. Next time is C. So C, because A page frame 1 and page frame 2 already occupied, you have to remove either A or B. So you have to remove either A or B because A is the first in, because it's the first in, first out. A is the first in, so A has to be moved out. A has to be moved out, and C will enter the page frame. So this swapping or interrupt will cause a page fault, and then goes back to A. Since B is the first in, okay, if you compare this one, B is the first in rather than C, so B will have to move out. Here you put A here, then this remains C. And then the next one is B. This is considered a page fault. Okay, this is considered a page fault. Okay, now B. B has to enter. B has to enter, and then the first one that coming in, C or A, is C, because C coming first. So C has to be removed, replaced by B, and you enter A. So this is a BA. This again is a page fault. Each time you have to swap or interrupt, it is a page fault. And then D. D has to be entered and one of it has to be removed. So A is the first in compared to B is the most recent one. A is the last in, first in. So A has to be removed. So you put here D and you put your B. So this is the page fault. Second one, B already in the memory, so it will not increase. It will not cause a page fault. This one is okay. This one is okay, and this one also is okay. Now A has to enter in. Compare which one it has to remove. Okay, which one is entered first, B or D? So you can see here B is entered first, so you have to remove here B. You put A, and this one D, you remain D. And now C. This is a page 4. And now C have to enter, and no C in the main page frame in the memory, page frame 1 or page frame 2. So which one is the first in? First in is D. Okay, A is the most recent. D is the first in, so you have to remove D. This one you put A. So this is the page 4. And the last one, D has to enter in, and one of the page frame jobs, one of the jobs have to be removed, either page frame A1 or page frame 2. So you go to the first in is A, C is the most recent, so A have to be removed, D, and here you put C. So this is the page 4. If you see here, only two where B and where jobs is already reside in the memory are the page frame 1 or page frame 2. So this is the success rate. If you see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the success rate is 2/11, and the failure rate or page fault, we call it 9/11. 9/11. All right. Page interrupt. Term is we use page interrupt or page fault generated when a new page is brought into memory, whether the page is swapped out or not. Say 9 interrupts out of 11 page requests due to limited number of page frames. The failure rate is 9, 11 or 82%. Okay, this one is 82% failure rate, and success rate is only 18%. This is unacceptably high failure. So first in, first out. Anytime a page interrupt happens, it will increase more time. It's resource consuming, it's a time consuming. So your goal is to reduce the page fault or page interrupt. Okay, for the least recently used memory management, it's different from the first in, first out. So similarly, we just write down, okay, A, B, A, C, A, B, A, B, A, C, A, B, A, B, A, C, A, B, B, A, C, A, B, D, B, A, C, D, D, B, A, C, and D. Okay, A, B, A, C, A, B, A, B, A, C, A, B, C, A, B, D, B, A, C, D, D, B, A, C, D. So you have here okay, you have here page frame 1 and page frame 2. So the first one definitely A, and this one is definitely B. So this one, both of these have the page fault. Okay, for the third one, this one A, so it doesn't, not a problem. A already in the page frame 1. Now you look at number 4 is C. So C, you have to replace either A or B. So when you look at the list recently, you can see A the most recent and B the least recently used. So we replace page frame 2 B with C, and this one A, and this one is a page fault. Okay, and now you see A. You see A, it's not a problem. AC. Now you see B. So you look here. So B here, the most recent most recent data is A, and the least recent data is C. So you replace C with, because C is the least recently used, so you replace C with B, and this one you maintain A. So this is a page fault. Now you have D. So you look again. So D, the most recently used is B and least recently used is A. So you replace A with D. And then this one is maintain B. So this is a page fault. Then you have here B. So it's not a problem. B is already in page frame 2. Now you have A. So you look again. And most recent is B. And the least recent is D. So you replace D with A. And this one you maintain B. And then this is a page fault. And this one C. You look again here. The most recent data is A, and the least recent data is B. So you replace here B with C, and this you maintain A. This is a page fault. And then the last one is D. So you look again here. C the most recent data and A the least recent data. So you replace A with D, and this one you maintain C. So you have here 1, 2, 3, 4, 5, 6, 7, 8. So the failure rate is 8/11 and success rate is 3/11. So it is better from the most recently used. So these are least recently used. So there is also a variation of LRU, which is the clock page replacement policy. It is implemented as a circular queue and use a pointer to step through the reference bits of the active pages, simulating a clockwise motion. Okay, simulating clockwise motion. Circular queue use a pointer to step through the reference bits. So it will look on the reference bits. A page is selected for replacement if its reference bit is 0. So if 0, it will definitely be selected for replacement. If the reference bit is 1, the page is given a second chance and the reference bit is set to 0. If the reference bit is 1, you have to change to 0. First, you look at the pointer. Use a pointer to step through the reference bits of the active page, simultaneous clockwise motion. Okay, let's look at these examples. Okay. So in A, the pointer indicates the page that will be considered next for removal. So this is a pointer. This is considered for the next removal. Okay. So if you look at this, if reference bit is 1, the page is given a second chance and reference bit is set to 0. So page selected for if reference bit is 0. So since this is 1, you have to change it to 0. Okay, 1, you have to change it to 0. Then you look for the next one. This one 1, you have to change it to 0. Again, this is 1, you have to change it to 0. When it is 0, you replace. When it's 0, you replace with 1 and you change this to 146. So this page number is changed to 146. Okay? And then 1 remain 180. Okay? Because you already changed. On the previous page numbers. And then you have to put 146 here. Replace 146. Replace 210 with 146. So when page 146 is swapped in, reference bit will change to 1, 0 to 1, according to this. The page if its reference bit is 0, so change to 1. If reference bit is 1, the page is given a second chance, reference bit is set to 0, so it's not changed until the page number 0. You change and then you replace it with 1. Okay. This process continues, okay, until a reference bit 0 is found. From here, the process is continue process is continue until reference bits of 0 is found. In this case 111 until here 0, then it will replace the page numbers with a new value and so on. All right. So there is another version of a list recently used. Use the 8-bit reference and a bit shifting technique to track the usage of pages in memory. When a page is first copied into a memory, the leftmost bits is set to 1, remaining bits are set to 0. As the time ticks, the memory manager shifts every page reference byte to the right by 1. So each time page is referenced, the leftmost bit is set to 1. The shifting and the setting the leftmost bit when the page is referenced give a history of page use. So you have use a 8-bit reference and a bit shifting technique to track. So when a page is first copied into memory, the leftmost bit is set to 1 and remaining bit is 0. So 1, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. At each time the memory shift every page reference by byte to the right by 1. So the next time scale, supposedly 1 will move here, 0 will move here, and so on. So this one, the first bit depends on whether it is whether each time page is reference. Okay, if it's not reference, it remains 0. If reference, is set to 1. So this shifting and setting the leftmost bit when the page is referenced give a history of page use. So look here on this side. So on this one on section A, you have here all this initialized to 1. Okay, remember this one? When a page first copied into memory, the leftmost bit is set to 1, remaining bits are set to 0. So this is an initialize. Okay, so this one you can see like page 1, page 3, 1, 3, page 5 and 6 are referenced, while page 2 and page 4 are not referenced. So page 2 and 4 are not referenced, so it remains 0, and the bit shift and the 1 shift to the right. All these page number bits on the leftmost bits will shift to the right. Those who are referenced, the leftmost bit will change to 1. Sorry. So sorry. This one 1, 3, 5, 6, and this like 1, 2, 1, 2, and 4 are reference. So 1, 2, and 4. So you see the leftmost. Bit. And next time it will all this will shift to the right. This is 1, 2, 4, and this is 1, 2, 4, and 6. 1, 2, 4, and 6, and this one is 1 and 4. 1 and 4. 1 and 4. So this is the least recently used of 8-bit reference. Now the one with the smallest reference byte value is the one least recently used. So the one with the smallest reference byte value is the one least recently used. Okay. So the values stored in the reference bytes are not unique. It's not unique. You can see here from this the last value is 3 and 5. You can see like 3 and 5. 3 and 5 have the same value. In this case, the least recently used or LRU policy may opt to swap out of all the pages with the smallest value or may select one among them based on other criteria as first in first out priority or whether the content of the page have been modified. So either you want to select 3 or 5. It depends on the policy that you created. Okay. It may opt for the pages with the smallest value or might select one among them based on the other criteria as first in first out priority or whether the content of the page has been modified. So you can say that the memory manager, okay, so these are mechanics of paging. So what is the mechanic of paging? The memory manager needs a specific info about each page in memory in order to swap page out. Of course, you have a memory here. Then you have a page frame number. So memory manager needs specific info about each page in the memory or the OS. OS need a info about each page memory in OS in order to swap page out. So this is a job with a page number, page 0, page 1, page 2, and so on in order to access the memory. So this is OS. Uh, you have here page map table for job 1 from the slide 12. Okay, you can refer to the slide 12. You can refer to the slide 12. Wait. Okay, for job 1, you have page 0, page 1, page 2. So page 1, job 1, page 0 at frame 5, frame 7, frame 9, and frame 12. So 5, 9, 7, 12. So status bits, because all this in the memory, the status bit is active 1. Reference bit, only 1 and 3. The reference bit indicate whether a page has been referenced recently and is used by the LRE to algo to determine which page should be swapped. So it's 1 is used recently, okay? It is used recently. 0 mean it's not least used recently, so this will be swap out, okay? Those who use recently will not be swapped out. So this modified bit, uh, modified bit, whether you have to modify the page, the frame number. If modify, you put 1, or if not, you put 0. And this is the page frame number. Okay, for first in, first out, it only look on the status. If FIFO, when you use FIFO, you only use on the status and modified bits. Okay, FIFO, status, and modified bit. But for LRU, it use a status bit, reference bit, and modified bit. So let's recently use all this in order to make a swap. So which page LRU policy choose to swap out? Case 1 is the ideal candidate. Okay, it's not modified, no reference. The page need not be rewritten to the secondary storage. So it's not modified as a reference. So like this is the memory, this is the RAM, and this is the secondary storage. So this you need not to write anything to the secondary storage. No need, because it's not very modified, it's not being referenced. It's the ideal case. The next most likely candidate is case 3. It has been modified. It's not been it's been modified. By being modified, the page has to be swapped out. So the page must be swapped out and returned to the secondary storage. And then case 2 is the third choice. Okay, it's not been modified, but it has been referenced, used. And case 4 is the most unlikely choice, modified and reference. Okay, if following order, this is the case, this is the 1, 2, 3, and 4. This is what LRU, page LRU choose to swap out. Case 1 is the ideal one. Case 2, case 3 is number 2. Case 2 is number 3, and case 4 is number 4. So a failure to find a page in memory is called a page fault. The working set page fault or interrupted. See, you remember like A, B, A, C. So this is the, sorry, page frame 1, page frame 2. So this one A, this one page 4. Failure to find a page in memory is called a page 4. So here A. So this is failure to find a page in the memory is called a page 4. C, this is what is a page 4. Say A and B. So if you use a first in file or least recently used, you have to remove a B. Okay, C and A. Failure to find a page in memory is called a page 4. So we introduce a working set. The working set of a job is the set of pages residing in memory that can be accessed without incurring a page fault. So the goal is to minimize the page fault. The working set is a way or set of jobs that residing in memory that can be accessed directly without incurring a page fault. It will be convenient if we could load all the pages of a job's working set to minimize page faults and to speed up processing. Of course, this is an ideal way. If we could load all the pages of a job's working set to minimize page faults and to speed up processing. So when it happens, the page faults, you have to swap. It increases the time consuming. It is a complex and it is increase the workload of the memory and of course the CPU. If you don't have a page fault, you can speed up your processing or jobs. Okay, here you have two issues. How many pages comprise the working set? It's actually difficult to determine based on the job's applications. What is the maximum number of pages the OS allowed for working set? It is important in time sharing system that regularly swap jobs pages between memory and secondary storage to accommodate many users. Okay. It also creates a problem where each time a job page is reloaded into memory, it has to generate several page faults until its working set is back in memory and processing can continue. Still, you have a page fault. We can eliminate entirely the page fault. So, solution is begin by identifying each job's working set and then loading them into memory in its entirety before allowing execution to begin. Okay, identifying each job's working set and then loading them into memory in its entirety and all the jobs load into memory before allowing execution to begin. So this is this example of page fault. Incur high overhead. High overhead meaning the waiting time. So execute process take a standard 30 millisecond, but the page wait will take about 300 millisecond. Okay, this is the working set. Page fault incur high overhead and must be minimized as much as possible. So in a time sharing system, the OS must keep track of the size and identity of each working set and make sure jobs for processing do not exceed available memory. Okay. So the OS must be intelligent enough to track the size and identity of each working set and make sure jobs for processing do not exceed available memory. It's very important to to keep a small, basically a huge jobs is divided into a small chunks. Okay, or small chunks or smaller jobs. Some OS use variable working set size, increase decrease it as necessary. So OS use, I think most all OS use a variable working size and increase decreases as necessary. So what are the advantage of demand paging? It introduced the concept of virtual memory. It's not really a virtual memory. It means like you have a secondary storage, or you can call it cache memory. And hence, jobs are no longer constrained by the size of physical memory. Memory is utilized more efficiently because sections of jobs that are seldom used or not at all are not loaded into memory unless they are requested. Okay. Section of jobs that are seldom used or not at all not at all are not loaded into the memory. So this increase the efficiency of memory. You don't have to job that seldom used or not used at all. You don't have to load it into the memory unless they are requested. So the disadvantage is increased overhead caused by the tables and page interrupts. Tables and page interrupts. Your goal is to minimize the page interruptions or page fault. Of course, overhead caused by the tables because you have to manage a page map, a memory table, memory map table, page map table, the job table, and so on. Now we go to the segmented memory allocation. So each job is divided into segments of different sizes, one for each module that contain pieces that perform related functions. Okay, different size job into segment, different size, one for each module that contains pieces that perform related functions. This approach reduces page faults that resulted from having a segment loop split over two or more pages. Okay, so in before this you have a segment over page frame two, page two or more page frame. So you have a page fault if it doesn't have. You have to swap out. You have to swap in the memory and swap out the free up the least recently used job or first in first out. Main memory is not divided into page frames. Memory is allocated dynamically. So memory is not really into the page frame divided. It is allocated dynamically. So when a program is compiled, the segments are set up according to the program structural models. So you have here, this is a main programs or segment 0. And this program, each segment is number a segment map table and generated for each job. So you have here, a job 1. This is a job 1. Composed of a main memory, main program. This is a main program. This is a main program. And of course, you have two subroutines together with segment map table and actual main memory allocation. So this is segment 0 for main program, segment 1 for subroutine A, and segment 2 for subroutine B. Each segment is numbered and a segment map table is generated for each jobs. Okay, each segment is numbered: segment 1, 0, 1, 2, segment map table. Segment map table contains the segment numbers, segment length, access right, status, and its location in memory when loaded. So segment map table also contain reference, modify, and status bits. So you have a segment map table SMT. So the memory manager keeps track of segment in the memory using 3 tables. One is job table, one is a segment map table, and one is a memory map table. So segment map table is like a main program, subroutine of A, B till N. Okay. So job table is to list each job in progress. Segment map table lists detail about each segment, one for each job. Okay, one for each job segment. And then memory map table monitors the allocation of main memory, one for the whole system. So you have here a main program on segment 0. The size is 250 lines, 250 bytes. Status is yes, access is execution. And the memory location is 4000. And you have a subroutine A1, which is 200, 0 to 199 lines. Status yes, and the execution. And you have a subroutine B, where size is 100, status is no. and then you have subroutine B have to wait, okay, because there is no enough memory locations. So access is only execution, and you don't have a memory address allocation yet because segment subroutine B still have to wait until one of the segment is one of the either of the main memory is enough to allocate the subroutine B. So instruction within a segment are ordered sequentially, but the segment is not be stored contiguous memory. So it is execute in a sequentially, meaning that in order 0, 1, 2. But you don't have to put the segment, you don't have to store the segment contiguously. You say the main program is here and the subroutine A is here. Subroutine B because there are no enough space, so you have to wait other programs to finish. Yeah. Okay. So we access a specific location within a segment using an operation similar to the one used for page memory management. Okay. So you want to access a specific location. The addressing scheme requires the segment number and the displacement within the segment. So you have a displacement, 0 to 349 is 350. This one is 100, and this one is also 100. Okay. Since segment size may vary, the displacement must be verified to make sure it is not out of the segment range. So you have a segment 1 consists of all subroutine A. The system find the beginning address of segment 1 is addressed at 7,000. So segment 1 address at 7,000. Let's say the instruction requests the processing of, okay, instruction. You want to request a processing of line 100. Request processing of line 100 of subroutine A. Sorry, subroutine A. Okay. In order to locate that line in the memory has to add 100. The displacement at to 7,000. So you have here like 7,000 and call a subroutine A at line 100. So you have 7,000, you have to add 7,000, you have to add 100, so it will call subroutine A is located at 7100. Okay. In order to locate the line memory, the memory manager has to add 100, the displacement to 7,000, beginning address of segment 1. So you add here 100, call subroutine A. Okay. And for subroutine B is plus another 100, so that 7199. Okay. 0 to 199. So this is 700. And this is 7199 for call subroutine B. So what is the difference between paging and segmentation? Page are physical units that are invisible to the user's program and of fixed size. So invisible to the user's program and in a fixed size. Segments are logical units that are visible to the user's program and of variable sizes. Okay. Pages are invisible to the user's program and of fixed size, and the segments are logical units that are visible to the user's program of variable sizes. And you have a segmented demand page allocation. This is the last techniques. First, you have page demand. First, you have what we call that page allocation. The second one is a demand paging allocation, segment allocation. So this is a combination of page and segmented. Each combination of segmented domain paging offers the logical benefits of segmentations and the physical benefits of paging. So you have both of best of both worlds, the logical and the physical. A segment is subdivided into pages of equal size, smaller than most segments, easier and is easier to manipulate. It overcomes the problem of segmentation such as compaction, external fragmentation, and secondary storage handling. Okay, it overcomes all these problems of compaction, external fragmentation, and secondary storage handling. So you have four tables. The first one is the job table, segment map table, SMT, page map table, PMT, and memory map table. So this is the example of this one. And this is the active job table. You segment it into job 0, job 1 until job n. And then job 0, you you classify into the page map table, job 0 segment 0, job 0 segment 1, job 0 segment 2, and job 1 segment 0, and so on. So you have active job table, job number. This is the first job table. This is segment map table where you put job, you break down into several jobs, and these several jobs you reduce down, or you classify down to the number of segment, and all this is loaded into the main memory. In addition to the info shown in the diagram, segment map table also contains info regarding protection. Okay, segment map table. Segment map table info about the protection. Read, write, execute. Either you read, write, execute, or delete file permission. Okay. PMT also contains the status modifiers and reference bit. So this okay, the usual the usual status modified bit and reference bit. To access a location in memory, the system must locate the address that is composed of three entries: segment number, page number within the segment. So segment number either job 0, job 1, job n. Then it's a page number within the segment, meaning that segment 0, job 0, segment 0, job 0, job 0, segment 1, and so on. And within and displacement within the page. So this is a displacement within the page. Displacement just from 0 to 99 is actually 100, 1 to 100. So there is a major disadvantage of a segmented demand page memory allocation. The overhead requires for an extra table. So usually you have 3. Now you have 4 tables. The time required to reference the segment map table and page map table. So segment map table and page map table. Time required is actually a lot, actually, because you increase the complexity. Solve it, use the associative memory to minimize the number of references and speed up the process. So associative memory is a set already allocated to each active jobs. Okay, associative memory is a set of registers allocated to each active job. The associative registers associate several segments, so it's take several segments, and page numbers belonging to the job being processed with their main memory address. Okay, what does the associative register or AR do? It associates several segments and page numbers belonging to the job being processed with their main memory address. Okay, it resides in the main memory. The number of registers varies between systems. So associative memories resides in the main memory or RAM, and number of registers varies between systems. So when a job is allocated to the CPU to process, The segment map table is loaded into the main memory. Segment map table is loaded into the main memory, and PMT is loaded as needed. So the PMT, if you need to load into the memory, store the memory, you have to from the page map table will be loaded to memory based on the requested, okay, on demand. As pages are swapped between main memory and secondary storage, all tables are updated. When a page first requested, the jobs segment map tables is searched to locate its PMT. So remember PMT, job 0, job 0, job 1, and so on. So you have a PMT segment map table, job 0 segment 0, job 0 segment 1, job 0 segment 2, and so on. So the job assembly is searched to locate its PMT. The PMT is loaded and searched to determine the page locations in memory. If the page is not in the memory, a page interrupter is used or page fault, and the page is brought into the memory and the table is updated. Okay. So the first one is a job in the segment map search to locate PMT. The PMT is loaded and searched to determine the page location in the memory, loaded into the main memory and determine the page location, the address. And if the page is not in the memory, you cannot find, a page interrupted or page fault is issued and the page is brought into the memory. And then the table is updated. So since the segment's page map table now resides in the memory, another request for pages within this segment can be quickly accommodated. So if like segment of PMT already resides in the main memory, so another request for pages within this segment can be quickly accommodated. Okay. So within the segment within this PMT is can be quickly accommodated. So accessing SMT and PMT is time consuming. SMT memory overcome this drawback by storing info about the most recently used pages in memory. When a page request is issued, two searches are initiated through SMT and PMT to the content of associative registers. If the search of SMT memory fails, no time is lost because the search to SMT PMT has already begun. Okay. Remember, if the search of SMT memory fails, no time is lost because the search to SMT and PMT already begun. If the search accelerator is successful, the search through the tables are stopped. And okay, whenever the accelerator is successful, stop the search throughout the tables and address translation is performed using the info in the associative registers. One example is 8 SMT registers per job. We'll use them to store the SMT and PMT for the last 8 pages referenced by that job. When an address needs to be translated from a segment and page numbers to a memory location, address needs to be translated from segment and page numbers to a memory location, the system looks first in the 8 associative register. If a match is found, the memory location is taken from the register. Otherwise, the search is PMT SMT continues. Okay. So, in a nutshell, virtual memory makes possible to swap page between main memory and secondary storage. It gives user the impression that their entire program is loaded into main memory when only a portion of it is actually loaded. So you have your main memory and you have your secondary storage. Possible swap. Okay, this is what it is. Secondary storage is considered as a virtual memory. Prior to virtual memory, program are responsible for making sure program fits into available memory. So last time programmers are responsible for so everything is depends on the programmer to make a small chunk of the big jobs so that it can fit the memory. So programmers have to do all the hard work. So this is the difference between virtual memory with paging and virtual memory with segmentation. So with paging, it allows internal fragmentation, while the virtual memory doesn't allow the internal fragmentation. Paging doesn't allow external fragmentation, while the virtual segmentation allow it. Programs are divided into equal size pages, unequal size segments for segmentation. Absolute address calculated using page number and displacement. Absolute address calculated using segment number and displacement. So you have a page number here, but now you have a segment number. And requires PMT and requires segment map table. Segmentation allows user to share program code. A shared segment contains an area with unchangeable code. Reentrant code is stored. So this one you cannot change. It's maintained here. Several data areas, one for each user. Users share the code which cannot be modified. This one, the code cannot be modified. And they can modify the info stored in their own data areas. They can only modify the info stored in their own data areas as needed without affecting data stored in other users' data areas. Okay, each user can only modify the info stored in their own data areas. Can only modify info stored in their own data areas. Before virtual memory, sharing involves sharing copies of files in each user's account. Users load their own copy and work on it anytime, creates a great deal of unnecessary cost. So overhead of loading the copies and the extra secondary storage is needed. So you have an overhead of loading the copies. That's why you need an extra secondary storage. So virtual memory reduce the cost substantially because shared programs and subroutines are loaded on demand. So shared programs and subroutines are loaded in demand. Okay, it reduces storage requirements of main memory. So you don't have to put entire jobs into the main memory. You only require the on-demand one, the one that you need to process. Using virtual memory also involves cooperation between memory manager, tracks each page segment, and processor hardware. Issues the interrupt and resolve the virtual address. So one of the example is the page. If a page that is needed is not in memory, the processor hardware issues the page for a memory manager choose a page frame, loads the page and updates entire entries in the memory map table and the page map table. So if page that is needed not in the memory, the processor hardware issues a page fault or page interrupt, and memory manager choose a page frame, loads the page and updates the entries in the memory map table and page map table. So advantage of virtual memory management is job size is not restricted to the size of the memory. Memory is used more efficiently because only selection of jobs that are immediately needed are stored in the memory on demand, and allows an unlimited amount of multi-programming, multi-jobs, multi-processing. Okay. So advantage of virtual memory again eliminates external fragmentation and minimize internal fragmentation by combining segmentation and paging. It also allows sharing of code and data, facilitate dynamic linking of program segments. So that's all for today. Thank you very much and have a good time.